So here's somewhere where we've been. So we've been talking about vector line integrals. And as we talked about, they can be over curves, not just lines. And then new thing is vector surface integrals. So if you have for a vector line integral, you have some vector field. Maybe it looks like this. Here's your vector field. And for the purposes of this beautiful picture, we'll assume our vector field is in the plane. And you can think of this vector field as being like wind. A nice wind. We have a nice windy day here at Swarthmore. And you are maybe here, you're here in classroom 104, and you wish to have lunch over here at Sharples, and you're going to walk there. Not in a straight line, because that's not how paths work, and here at Swarthmore. But maybe you'll go something like this. Maybe that's your path. So that's the pink is our vector field F, and the C is our oriented path that we're going to take to get to lunch. And so a vector line integral is the integral over C of F dot ds. And here ds, this is all review, so what is a little bit of oriented line segment in the direction that you're going. And you add these up at each point. So here the dot product between these things is 0, meaning that the wind is not helping you or hurting you. It's just like a crosswind hitting your right arm. So here it would be 0 approximately, but up here I'll draw in an extra vector field vector, like maybe it looks approximately like that. The dot product would be positive, the wind is at your back, it's helping you get to lunch, you're going to get in line first, you're so happy, this is good. So this is a vector line integral. And now, let's talk about vector surface integrals. So this, I drew this as being in the plane, but wind is really three-dimensional, and you can imagine if you were like Harry Potter on your broomstick flying to lunch, you could do the same thing. Take the dot product at each point, figure out the best way to get there. So, what?
Oh, sorry.
Yeah? So then a vector surface integral is fundamentally in 3 dimensions. So I like to, whereas here I like to think about wind, for vector surface integrals I like to think about water. So we have some vector field, maybe I'll draw it looking kind of the same. But you can imagine that this is like water in a turbulent stream. So you could imagine that like the whole classroom here is full of water and it's flowing in some way. And you can see it because maybe there's like minnows or microplastics or something in the water, so you can see where it's going. Yeah, you all are hopefully obsessed with microplastics in the water, just like I am. There's so many microplastics in the water. It's so bad. But anyway, it helps us to see which way the stream is going, so not so bad. For us mathematically. Yeah, don't use straws, don't wash your synthetic clothing. Life is hard. So you imagine that this is a stream. This is our F. And then we put some kind of net in our stream. So how shall our net go? Maybe our net is something like this. And this is, you'll have to use your imagination to imagine that this is a 3-dimensional net. But now I've put a net into my stream and I want to catch minnows or microplastics or something. So what you do here, that was a vector line integral. This is a vector surface integral. Here's my surface S. We take a surface integral over S of F dot B, in this case, big S. That was a small s. This is a big S, because this is a little bit of oriented line segment along a curve, and this is a little bit of oriented surface. So you can think of ds as being a little patch of area with an orientation. So last time we talked about picking an orientation, and that there's 2 that you can choose. Like on this line segment, on this curve, we could have gone 2 Sharples, or we could have gone back. There's 2 orientations to choose. Here, there's 2 orientations to choose. You could choose like basically to the right or basically to the left, different normal vectors to the surface. And so at each point, you would be adding up the dot product between the vector field and your chosen normal vector to the surface. So here it would be positive, here it would be slightly less positive, and we'd add those up over the whole surface. This is, so I think of this as like the net flow through the surface, and I say surface here because it gets a little bit tricky if you say the net flow through the net. And this is what physicists call flux, because you can imagine this is an electric field, and this is a surface. And over here, this you think of as like the net amount that you are helped or hurt by the vector field, and physicists call this work. So that's kind of going from one to the other, yeah.
If we take kind of the example that we were using last class, like the bubble that we blew up from a circle,
Yeah,
so flux is related to like the perpendicular area vector, right? Or
yep,
just the perpendicular whatever. So if we take like the circle that we had before, and let's say it's going I don't know, counterclockwise.
so we had a circle going counterclockwise.
Yeah.
Here it is.
And then we inflate it to create our surface.
Okay, then we inflate it to create a surface, maybe up or something.
Yeah. So, does that mean that, first off, the area vectors are going out on that one?
Yep, if we wanted to have a compatible orientation between our surface and our curve, our normal would be
So
like
then, for that particular curve, flux, positive flux would be from the inside going out.
Yep, if we wanted positive flux over the surface, we'd have to have field vectors going from the inside out.
So is direction for the surface of like the orientation something we arbitrarily define? Or is that something that'll normally be like part of the problem?
It'll normally be part of the problem. It'll say something like, calculate it with the surface oriented outwards, something like that. But in real life, you would choose it in a way based on what you cared about. Like here, if the stream is generally flowing in one direction, you would probably choose that to be your positive direction. Or if you're trying to catch fish, you would choose like the direction in which you're catching fish to be the positive direction, something like that. If you choose the opposite, it just comes out negative.